black hole to develop. However, such enormous stars have never been seen before in the observable cosmos. Even the heaviest star ever found is only about 300 times as big as the Sun. Additionally, there is no known process that can currently propel the creation of stars with masses many times that of the Sun. But we also know that circumstances in the early cosmos were different from what we see now. As a result, such stars could have developed in the early cosmos, as shown by simulations. Massive stars might have developed at the intersections of strong streams of dense and turbulent cold gas, but this would have been an extremely uncommon occurrence. However, in order for stars to develop, extremely bizarre circumstances would have had to exist, such as strong ultraviolet radiation or supersonic movements between gas and dark matter. To make matters worse, none of these out-of-the-way places have circumstances that are even remotely like those in which the first quasars were discovered. In that case, how do we account for the emergence of quasars? Scientists simulated the flow of the gas to get an idea of the solution to this query, but that the creation of typical stars, like the ones we see today, was inhibited by the turbulence produced by the stream's intersection. This instead caused the cloud in the simulation to expand so large that it disintegrated violently into two enormous stars, nearly 31,000 and 40,000 times the mass of the Sun. A supermassive black hole, billions of times the mass of the Sun, can develop and expand in just a few 100 million years if the gas from the streams continues to fuel the clouds. This explains how, even in the absence of unusual circumstances, supermassive black holes could have developed at the crossroads of gas streams. And if the numbers hold, about 200 quasars were born in the first billion years of the universe's existence. It's possible that we've figured it out now. One of the study's authors, Daniel Whalen, put it this way: the first supermassive black holes were merely a natural result of structure formation in cold dark matter cosmology's offspring. The edifice of knowledge we've erected regarding our universe encompasses its origins and contemplates its eventual conclusion. So, where does our narrative commence? Let's embark on this journey from the very outset. Let's delve into the genesis, starting with the monumental event known as the Big Bang. The concept of the Big Bang serves as a framework for understanding the cosmic evolution, an unfolding narrative that illuminates how the universe transformed in the blink of an eye. The very nature of what sparked this cosmic genesis remains an unsolved puzzle to this day. As we peer into the vastness of the universe and contemplate distant galaxies, a mesmerizing panorama unfolds. Everything appears to be receding from us, propelled outward at astonishing speeds. We string that all the way back, we glimpse a singular moment, perhaps 13 or 14 billion years in the past, where all matter was inexplicably condensed into an inconceivably dense point. The Big Bang stands as our prevailing theory, a testament to our attempts to decipher the universe's inception. For an extended period, quantum theory has solidified its place in our understanding of the universe. It hasn't yet unraveled all the mysteries science seeks to answer about the birth of our cosmos. Conventional Big Bang theory remains silent on what triggered the bang, why it occurred, or what transpired before. At this very moment, we find ourselves in the aftermath of the Big Bang. Everything what we see and hear and taste and smell and touch is aftermath. This is the Earth, a marvel of silicon and oxygen encasing a metallic core. Its surface is dominated by vast oceans, fostering a diverse array of life. In a rhythmic dance, the Earth completes a full rotation every 24 hours, while encircling the radiant star known as the Sun. completing an orbit every 365 days. The Sun, a radiant giant predominantly composed of hydrogen and helium. With a scorching surface temperature nearing 10,000 degrees Fahrenheit, this cosmic powerhouse converts a staggering 700 million tons of hydrogen into 695 million tons of helium every second. This celestial luminary is at the heart of our solar system, which took shape approximately 4.5 billion years ago. This system has 8 planets, from the sweltering Mercury to the frigid Neptune. Our solar system is no static entity, hurtling through space at a staggering 134 miles per second. It is part of a vast congregation of stars and stellar systems. This congregation, known as the Milky Way galaxy, around 200 billion stars. Among these, an estimated 6 billion may harbor planetary systems akin to ours. Our solar system, orbiting the center of the Milky Way on one of its outer arms, is just one member of a grand ensemble. The Milky Way is merely one among the vast expanse of more than 125 billion galaxies, constituting the observable universe. Indeed, the universe is colossal, and its enormity continues to expand. If we rewind time, we can witness the universe contracting, shrinking from a cosmic scale to a galactic one, then to the dimensions of our solar system, and further still, until everything is confined within the confines of a studio, a coffee cup, and ultimately an atom. The vastness of the universe unfolds before us, a cosmic narrative expanding across unimaginable scales. Physicists have pieced together an approximate timeline of significant events in the cosmos's existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant timeline of significant events in the cosmos's existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit, or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances. In both terrestrial atom smashers and the early cosmos, the challenging to achieve condition only lasted for a few fractions of a second. The early epoch, the subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected across space without interacting with anything. The first atoms, protons and neutrons, fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet, this procedure ceased as the temperature dropped. As temperatures settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this epic first identified in 1965, was created when photons that had previously collided with electrons were able to flow without being disrupted. The Dark Ages. There was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic dark ages refer to this time frame of around 100 million years. Because practically all of what astronomers know about the cosmos can be gleaned by studying starlight, this era remains exceptionally challenging to study. It's hard to piece together what happened if there are no stars to guide us. The first stars. The first stars were formed when hydrogen and helium began to compress into massive spheres, some 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's hard to put a time limit on reionization, as it happened so soon after the Big Bang. Its signals have been masked by subsequent gas and dust. Thus, the most that scientists can determine is that it was finished by around 500 million years after the Great Bang. Large-scale structure. Almost a billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars, visible from 12 billion light years away, switched on and began emitting their bright beams of light. The universe's middle years. Throughout the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result of them slowly expanding into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. A yellow star with rings around it formed from a cloud of gas around 4.5 billion years ago in one galaxy. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the sun retained a lot of water via this process, or it received a deluge of ice and water from comets later on.